Welcome back, everybody. In this video, we're going to talk about representing forces as vectors. And this unit is going to be very similar to the previous unit, where we were taking vectors, adding them, and then finding the resultant. But now these vectors are going to represent more real-world scenarios, and we're going to start off with forces. Now, forces, they are measured in units called newtons. So let's start off with a simple example. Let's say that we have an object here, and it is being pulled in this direction, or pushed in this direction, by two forces. So let's say that one force is pushing it 40 newtons. And then we have another force pushing it. Let's say it's pushing it at half of this force, which is 20 newtons. So what's going to happen to the object? Well, 40 newtons plus 20 newtons, it means that this object, if we draw here again, it's going to be pushing in this direction at what? At 60 newtons. So we call this here the resultant force. So basically the force, the resulting force that happens when you add up all of the different forces acting on an object. Now, something that you're going to see coming up in this unit pretty often is the concept of an equilibrium force. The way I like to think about it, it's basically the force that brings everything into equilibrium. So basically, equilibrium happens when nothing moves, so when no object moves. And another way to think about the equilibrium force is basically the force that is the same magnitude and opposite direction of the resultant force. So going back to this example, we had two forces acting on this object, 40 newtons and then 20 newtons going in the same direction. So the resultant force was 60 newtons. So what's the equilibrium force going to be? It's basically going to be the force that makes the object not move. Right now, this object is moving 60 newtons in this direction. So what's the force that will make the object not move? Well, it's going to be a force with the same magnitude as the resultant, but in the opposite direction. So this here, 60 newtons, this here is going to be the equilibrium force. So if we take these two forces, add them together, 40 newtons plus 20 newtons, and then on top of these, we add the equilibrium force, which would bring it back to the starting position. Whenever you come back to that starting position, it means everything is in equilibrium, nothing is moving. And the equilibrium force is what's going to make that happen. Let's try another example. So let's say that we have an object here, but now there are two forces acting on it. Let's say one force is acting on it at 140 newtons in this direction. And then let's say another force is acting on it 100 newtons in the opposite direction. Right? So instead of both forces being in the same direction, they're now going in the opposite direction. So this sort of represents almost like a tug of war on this object. There's one force pulling it 140 newtons this way, another force pulling it 100 newtons this way. Well, what's going to happen? Well, to find the resultant force, what you do is you basically take these forces and add them up. And when you're adding vectors, these forces are represented as vectors, you got to add them tail to head. So if we take this force, 140 newtons, And then from that force, we're going to add this 100 newtons going in the opposite direction. So let's say that's like that. What's going to happen? Well, the resultant, if you remember, it's always drawn from the tail of the first vector to the head of the last vector. So it's going to look like this. Now, technically, these forces should sort of be like on top of each other, but I sort of spaced them out just so you could see clearly what is happening. So I took this 140 newtons, added this 100 newtons going in the opposite direction. Again, this 100 newtons should be on top of that vector. And then this here is the resultant. Force, or the resultant vector. So what's the magnitude of the resultant going to be? Well, 140 newtons minus the 100 newtons, how much is left here in this space? Well, 40 newtons is left. And that makes sense. So if an object is being pulled by 140 newtons in this direction, by 100 newtons in this direction, well, the resulting force, the object is going to move in the direction with the higher force, but not at that full 140 because there's still 100 being pulled this way. It's going to be moving at 40 newtons, at a force of 40 newtons. Now, what is the force that will bring everything into equilibrium? So this object here is not moving. Well, it's going to be the same magnitude as the resultant force, but in the opposite direction, like that. So this would be 40 newtons, and this would be the equilibrium force. Right? So if we added another force here of 40 newtons, which is the same as this equilibrium force, then the object wouldn't be moving because it's being pulled 140 newtons in this direction and 140 newtons in this direction. So everything would be in equilibrium and this object here wouldn't be moving. Now forces can get a little bit more complex when you start adding angles to examples. So let's say that we have an object here, and let's say that there's two forces acting on it. So one force, say it's 40 newtons acting on it this way, and then let's say there's another force, 30 newtons, acting this way. So these forces are perpendicular to each other, or there's an angle between them of 90 degrees. Now, whenever forces are acting on an object, the diagrams are always going to look like this. So you're going to have the object, and then attached to the object are going to be the tails of all of the forces acting on it. Right? So if you get an example or you're doing a question that's stated in words, you got to draw a diagram. The forces acting on an object, you want to always make sure that the tails of those forces or of the vectors are attached to that object. So now, if there's 40 newtons acting this way on this object, 30 newtons acting this way, what's going to be the resultant? Well, the way you find the resultant is you have to take both of these vectors and then add them. And when you add vectors, how do you do that? Well, we'll take this first vector here, 40 newtons, and then to add this vector, you need to attach it to the head of the last vector. So 40 newtons plus 30 newtons here, like that. And so the resultant is going to be this dotted vector here. So this is going to be the resultant. Let's just call it vector r. And now that we have this vector r, this resultant vector drawn, we can figure out a bunch of stuff about it. So let's start off by figuring out what's the magnitude of this vector going to be. Well, notice that because this is 90 degrees, these vectors are perpendicular to each other, and then we shifted this vector over. Well, it means the angle here is going to be 90 degrees as well. So notice to find the magnitude of this resultant force, we can just use Pythagoras' theorem because this resultant force is the hypotenuse in a right angle triangle. So basically the magnitude of the resultant squared is going to be the magnitude of this vector squared plus the magnitude of this vector squared. Adding these up, you'll end up getting 2,500. That will be the magnitude of the resultant squared. Square root both sides to get the magnitude of the resultant on its own. And we get 50 newtons. So this resultant vector here has a magnitude of 50 newtons. Now, if you remember, vectors usually have two things. They have a magnitude, but they also have a direction. And in this case, there's going to be an angle here that we can solve for. So basically this resultant, which is going to go this way, it's going to go on an angle to or from the 40 Newton force and the 30 Newton force. So we could figure out first what this angle is going to be. What's the angle of this resultant force relative to the 40 Newton force? And again, since this is a right angle triangle, you can just use SOHCAHTOA. So notice that tan theta is what? Opposite over adjacent. So it means that theta is the inverse of tan of 30 over 40. And so when you do that in your calculator, you would end up getting approximately 37 degrees. It's going to be like 36.87, I think, but let's just round it to the nearest degree. So that angle here is 37 degrees. So this resultant vector is in a direction 37 degrees relative to that 40 Newton force. This force right here. This here is 37 degrees. Now, we could have also stated the direction of this resultant vector relative to the 30 Newton force. So notice that this is 90 degrees. If this angle is 37, then what's this angle going to be? Well, it's just going to be 90 minus 37, which would give us 53. So you can state the direction of this resultant either 37 degrees relative to the 40 Newton force, or you can say 53 degrees relative to the 30 Newton force. Right? But either way, it's the same thing. So this resultant force, remember this here, is all about the resultant force. So if there are two forces acting on this object, 40 newtons this way, 30 newtons this way, what's going to happen is the object is going to move this way along that resultant force vector, and it's going to be moving at a force of 50 newtons, either 37 degrees relative to the 40 Newton force or 53 degrees relative to the 30 Newton force. So this is all about the resultant force. Now, what's the equilibrium force going to be? What's the force that's going to bring everything into equilibrium where this object is not going to be moving? Because right now, it's moving 50 units in this direction. 50 newtons in this direction. Well, it's basically going to be the force that is the same magnitude as the resultant, but in the opposite direction. So this here is the resultant force. The equilibrium force, same magnitude, but in the opposite direction. So let's call this force here E for the equilibrium force. So the magnitude of the equilibrium force is going to be what? Same magnitude as the resultant force. It's going to be 50 newtons. But what is the direction going to be? Well, notice that since the equilibrium force is always going to be the opposite direction of the resultant force, the angle between both of them is always going to be 180 degrees. Basically, the resultant force and the equilibrium force will always make a straight line, no matter how the diagram is made. So the angle for a straight line, basically 180 degrees. So notice that we can talk about the direction for the equilibrium force relative to that 40 Newton force and the 30 Newton force, but let's just start off with the 40 Newton force here. So notice that this whole angle between the equilibrium force, resultant force, it's 180 degrees. Well, if this angle here is 37, then what's this angle going to be between the equilibrium force and the 40 Newton force? It's just going to be 180 minus 37. 180 minus 37 gives us 143 degrees. Right? So we can say that equilibrium force has a direction of 143 degrees relative to the 40 Newton force. What about to the 30 Newton force? Well, if we bring that 30 Newton force back here, so I'm going to just erase this. Say that we draw this 30 Newton force here again. If you remember, the angle here was 53 degrees. Well, notice that we can find the angle between the 30 Newton force and the equilibrium force as well. So we know that this whole angle between the resultant and the equilibrium on the other side, it's 180 degrees as well. 180 degrees minus 53, that would give us what? Well, that would give us 127 degrees. So we can say that the equilibrium has a direction either 143 degrees relative to the 40 Newton force or 127 degrees relative to the 30 Newton force. So sometimes questions can get pretty tricky when there are multiple forces acting on an object at certain angles. And you have to find that resultant, and then you have to find that equilibrium force as well.